Oh, Thai foo, nice. Hello, my name's Carl. Welcome back to my channel and welcome back to my workshop. Now, over the past few months, I've had a fairly extensive reorganisation in here to try and make things a bit more user-friendly and to make better use of the space that I've got. And that's led to a bit of a backlog with niggly little faults on some of my equipment. And one such on my compressor we're going to have a look at today. We're also going to look at some of the underlying engineering principles behind what we're doing, and we're going to be delving into the secret life of springs. So here it is. This is my generic Chinese made compressor, 240 volts, single phase, 3 horsepower, gives a maximum pressure of about 110 psi. It's a 100 litre unit. Restarts at about 70 psi. I use it for powering my air tools and the blowgun and that type of thing. And it lives underneath this bench to save space, really. It's got a decent footprint on it, so I don't have that much room in here, so I've built it into the underneath of the bench and just maximises the space I have got. I came in here one morning and there was a loud hissing sound coming from the compressor, and I discovered that the safety valve was blowing off. And I'll tell you exactly what happened to that in a second. So this is the safety valve, and this is the replacement one. The old one had actually half sheared off across the threads. There's a 1/4 BSP thread on the end of this brass portion that's threaded into this body, and the air was escaping through that gap where the threads had partially sheared. So I got this one, I fitted it, and I discovered that it was relieving at too low a pressure, about 70 psi. So I had to find some means, if possible, of adjusting this valve so that I could increase the point at which it relieved. And I'm going to show you how I did that in the course of this video. Now I've just tried a little trial to record the gauge on the compressor to show you the pressure that the blow-off valve's going off at, or the safety valve rather, and the vibration and noise is just horrendous. So I'm going to make up a little remote pressure gauge so that you can see it with not quite as much noise, hopefully. So we'll do that now. Just got a little 3/8 BSP to 1/4 BSP adapter. 3/8 BSP airline connection. Just put some Loctite 577 onto the threads. If I've got that, there we go. Let's get it open. Get some of that on there. We'll thread this in. Get that in there. Get that nipped up. Where's my 11/16? There it is. There we go. This is a very nice Swindon's vise that I restored and painted it up. I put some aluminium soft jaws in it. They're not posh ones like John of John's workshop with cross hatching on them. They're just plain, but they do a good job anyway. We'll put a bit more 577 on this, on the gauge. This is 1/4 BSP this side, so we'll thread that in. There we go. Let's give that a quick nip. And that should do the job. Right, so we'll be able to get this connected up. We'll have it in the vise and you should be able to see what pressure it blows off at. Don't worry, you'll hear it when it blows off. Okay, so we have our remote pressure gauge connected up to the compressor now, and give or take parallax error, you can see that it's sitting at about 55 psi there. Now, as I said before, the safety valve blows off at about 70 psi, which for me is about 30 psi too low. It shuts off again at about 60. So we'll see that when we switch on the compressor. and it is quite loud when it blows off. It makes like almost like a horn kind of sound, like someone practicing the trumpet who needs a little bit more practice. So I won't inflict too much of that on you when it does blow off, but you'll see the pressures that are involved, and I'll try and speak over the top of the sound and see if you can hopefully hear me. Okay, switching the compressor on now. Okay, so we're building pressure, 60 psi there now, 65, approaching 70, and there she goes, blowing off now. Switch off the compressor. So there we can see about 65 psi. It's starting to shut off. You can still hear the slight hiss of escaping air as the ball just reseats itself. So we'll take that safety valve off now, and we'll see if we can do something about that blow-off pressure. So off camera, I removed the safety valve from the compressor, and I put it in the vise so we can strip it down and have a look at its construction and see how it works. This brass portion here has a 1/4 BSP thread on it, and with some Loctite 577 I've threaded that into a 1/4 BSP to swage lock adapter, because I changed a lot of the plumbing on the compressor to swage lock just to make it more leak proof and a little bit safer. On top of here there's a split ring, which when you lift that up or pull it, it pulls the valve up off the seat against the internal spring and allows you to dissipate the pressure manually. And just out of sight around the corner here there's a small hole that the air escapes from. So I think if we take this split ring out, we should be able to remove this little red plastic cap, and we'll see what's underneath there. So I'll try and work around the camera as best I can and get this little split ring off. There we go, it's coming off. So that's the split ring off. We'll take the little red cap off and we'll see what we have underneath. Okay, that's the red cap off. Underneath there we can see we've got some flats here for a spanner, some threads and a little jam nut, and this is the stem of the valve. So we'll take that little jam nut off and we'll see if we can find out what's inside there. Okay, right, here we are, see what we've got. So just randomly picked up a 9/16 there, or actually no, it's a 14mm, and that is the size of the jam nut. So we'll undo that a little bit. I'm just wondering if this is going to be, yeah, that's hand tight, so let's unscrew this. My hand seems to be in the way, but we'll get it out. And what's in here? Okay, so we have got a little valve poppet. So there's a poppet with, that's kind of an elastomeric material there, almost like a neoprene rubber on the end of it. And we've got kind of a compliantly mounted stem there to allow that just to seat wherever it needs to. And then here we have the spring, the reference spring, and this body which has these flats on it. Now inside here is the seat. I'll see if I can show you that. Just put those parts down for a minute and see if I can. There you go. That's the seat there, just like a little brass ring essentially. It's hard to tell from that picture, but that ring is slightly raised above the rest of the annulus in there. So put that back in the vise. So looking at this, it's fair. I'll just bring this back into shot. You can see that spring fits over there. So that spring is pressing the neoprene poppet against the seat there, and then this this body sits over the top. So if we tighten that down some more, we're obviously going to compress the spring or preload the spring, and that's the adjustment. That's going to preload that spring against the seat, which is going to require more force and therefore more pressure to lift it off the seat and allow the air to escape and relieve. So we'll look into now a method by which we can connect this up to a source of pressure, and we can actually set the pressure that this blows off at, because as I said before, 110 psi is the shut-off set on the control switch, the pressure control switch on the compressor, and I want this to go at about 10% more than that, which is kind of a standard figure for compressors that for safety purposes is usually used. So I think that's going to be somewhere in the region of 120 psi. So we'll get something set up now to try and produce some pressure so we can adjust this, and we'll bring you back when we've got that done. This is the setup that I'm using to apply pressure to the safety valve in order to set it up. Now this is a Clark strong arm pump. It comes as part of a vehicle body repair kit, and it's capable of producing a pressure of about 10,000 psi, but it can produce as low a pressure as we want. We just have to be careful with the pumping of it. Now I always wanted a Tangy pump or an Enepac. They're your kind of go-to hand pumps really, I suppose, aren't they? But I couldn't afford one. They're ridiculously expensive. So this Clark one was a really good buy, actually. It was good value for money, especially as it came with a set of jacks, with it being a body repair kit. So that was really handy, especially when it came to moving machinery around in the workshop. Some of those jacks were really good for that. So what I've done to this is I've actually fitted some standard hydraulic unions to this, because it has got a 1/4 BSP fitting on or thread on the output there. So it's very handy for setting it up to do jobs like this, and it's really increased the usefulness of it. So I'll show you what I've got here. As you can see, we've got this 1/4 BSP fitting with a swage lock connector on it. We've got the gauge here. If I turn this round, you'll see how this is connected up. So what we've got there is a swage lock T, which has got a 1/4 BSP female thread at the top there. We've got the gauge into that. Then this end's got the pump on it, and the other end, which is currently capped, we'll put the safety valve onto there, and then we can pump up the pressure, and we'll see at what point it relieves at, and then we can try and do some adjustment. So I'll get the camera set up on the safety valve once I've got it fitted to this Christmas tree here, and we'll see how we get on. So here we have our Enepac-esque system for testing the safety valve relief pressure. Now we could quite easily set this by trial and error. Just thread the adjuster barrel into the body until we hit our pressure that we want of 120 psi. But what I want to do is take a closer look at this little unit and delve a little bit more deeply into how it works, and look at some of the underlying engineering principles that govern how this thing functions. Now, it's a fairly innocuous little unit, and you might think that's overkill to do that, but it may be small and it may seem insignificant, but there is quite a lot going on inside here once you get into the nitty-gritty of it. And it's also going to serve as a really good illustration for a kind of a thought process that I want to use in some of the bigger projects that I've got lined up for doing in the workshop. So that's what we'll do now. We'll have a look at how this thing works, and we'll look at that in some detail. And incidentally, I'm using my second best scriber here as a pointer. My other one's on loan to Terry Wogan. Okay, so I touched on briefly how the compressor safety valve works earlier on when I stripped it down and showed you the internal parts, and I want to go into that in a little bit more detail now. So here's a rough sketch of the internal working parts. So what you've got is the body, which is brass, and it has the 1/4 BSPP thread on the end of it. Inside it you have the poppet with its elastomeric seat, and that seats up against this brass seating ring. Then you have the reference spring, which is pressing the poppet against the seating ring. And then on the poppet itself you have the stem, which is kind of compliantly mounted so that can sit where it needs to. The stem is riding or guided by the hole in the end of the adjuster barrel, which threads into the body with this M12/1 thread. So that means every time we rotate this adjuster barrel 1 revolution, it translates inwards or outwards by 1 millimeter. Now, this brass seating ring here has a diameter of 5.5 millimeters, and I measured that with a drill bit, the shank of a drill bit, just by using it as a go/no-go gauge essentially. Now, the important thing to note about the basic principle of how this thing works is that the force due to the spring pressing on the poppet must at least equal the force due to the pressure against this surface area of the poppet here for this thing not to blow off. Once that force here overcomes the force of the spring, then the poppet's going to lift from this seat and the air or the fluid is going to escape from these outlet holes. So basically the pressure that's coming, or that's communicated through this line here, acts against this surface area of the brass seating ring, and that pushes the poppet to the left, and the force provided by the spring is pushing the poppet to the right against the seating ring. So what we'll do now is we'll have a bit of a closer look at this spring and see how we can work out how much force that can apply to this poppet. Welcome to The Secret Life of Springs Part 1. So we're going to talk about some of the terminology that's used to describe springs, and then we can move on to look at some equations and some principles that we can use to actually work out how much force they can exert. So obviously every spring has a length and a diameter, but the diameter that we're interested in here is not the OD that you might measure with a pair of calipers. It's called the mean diameter, and capital D, mean diameter, is equal to the OD minus small d, and small d is the wire diameter that the spring's made of. And we also talk about the number of active coils that a spring has got. Now, this spring in the picture here has 6 total coils, so that means it has 4 active coils, because the number of actual coils minus 2 gives you the number of active coils, and that's for a closed-ended spring. And what that means is a spring that hasn't just been chopped off, the end's been formed and made flat. So there you go, we have length, mean diameter, wire diameter, and the number of active coils. They're the main features of a spring that we're interested in for calculating how much force we can exert with it. This is part 2 of The Secret Life of Springs, and here we're going to look at the formula that we can use to calculate the spring rate, or the amount of force we get from a spring according to how much it's compressed. So I'm going to talk through this formula here in words now. So K equals G times D to the 4 divided by 8 times N times capital D cubed. So K is the spring rate, and that's measured in newtons per meter. G is the shear modulus of rigidity of the material the spring's made from, and that's measured in pascals, and it's the measure of the elastic shear stiffness of the material. N is the number of active coils. Now, for this type of spring, if it's closed-ended like the one we've got, then the number of active coils is just the number of coils minus 2. So if it's 8 coils, then it's 6 active coils. Capital D is the mean diameter measured in meters, and lowercase d is the wire diameter measured in meters. Now, it might seem strange measuring small spring diameters and wire diameters in meters and using big units like newtons per meter, but that's because we're working in SI units. So we have to use certain units and keep them square with everything else so that we get the correct answer. Now this shear modulus of rigidity, I've said here it's measured in pascals, but for materials like steel, we're talking about very big units for this, so it's usually mega or gigapascals. So now we'll go on to look at an example of how we can use this formula to work out how much we need to adjust our spring by to get the correct blow-off value for our safety valve. So how much force? And what I mean by that is, how much force does this reference spring here have to exert on the face of this poppet to keep it seated against the seat here against the pressure on the back of the poppet. Now we know that our design relief pressure is 120 psi, and that equates to 827 kilopascals or 8.27 bar. We're using pascals here as a unit of pressure because it's an SI unit and we need to keep our unit square in these calculations to get the right answers. So I measured the diameter of the seat with a drill bit, and I found out it was 5.5 millimeters. So that gives us an area of 23.7 times 10 to the minus 6 meters squared for this seat here where the pressure's exerting against the back of the poppet. So we now have 827 kilopascals against an area of 23.7 times 10 to the minus 6 meters squared. Now force is equal to pressure times area, so that's 827,000 times 23.7 times 10 to the minus 6, and that gives us a force on the back of here exerted by our relief pressure value of 19.64 newtons. Okay, now we've got a figure for the force that we're looking for from the spring. Let's have a look at our spring rate calculation that we mentioned earlier. So here's the formula. Oh look, Terry's back. K, our spring rate, equals G times D to the 4 over 8 times N times big D cubed. Now D, or lowercase d, on the spring that we've measured is 1 millimeter. That's the diameter of the wire. Uppercase D, the mean diameter of the spring, is 7 millimeters. The number of active coils, N, is 6 because it's 8 in total, so 8 minus 2 is 6. G, our modulus of rigidity, is 70 gigapascals. That's 70 times 10 to the 9 pascals. I'm using that figure, it's for cold rolled steel. It's on the reasonably low side, but I'm just assuming that this is a relatively low quality Chinese made small spring, like the type of thing you might even find in a pen, for example, that's being used in this unit. So we'll work these numbers into the equation now. So K is equal to 70 times 10 to the 9, that's our G, multiplied by 0.001 to the 4, because we have to put this millimeter figure here into meters for our SI system of units for these calculations to work out properly. We divide that by the constant 8 times 6, which is the number of active coils, times 0.007, which is our mean diameter in meters, cubed. And that gives us figures of 0.07 for the numerator of this calculation and 0.0000164 as the denominator. And that comes to, in newtons per meter, 4,270 newtons per meter. Now to put that into a figure that's more amenable for our usage with the small spring that we've got, that comes to 4.27 newtons per millimeter. And just to put that into context, what that means is 1 millimeter compression of the spring will give us 4.27 newtons of force. So now we know this, we can go and work out just exactly how many rotations we need on the adjuster barrel to give us the correct amount of force to get our design safety relief pressure. Okay, here we are. We've arrived at our destination after these long hard miles, the adjustment calculation. So we know the force required from the spring to balance everything out is 19.64 newtons. That's the force on the back of the poppet that's being produced by our safety relief pressure. The spring rate we've already worked out is 4.27 newtons per millimetre, and we know the pitch of the thread on the adjuster barrel is 1 millimetre, i.e. it gives us a 1 millimetre lead, so for every one rotation of the barrel we get 1 millimetre translation. So the number of turns of barrel, I should say. So the number of turns of the barrel is this force required, F, divided by the spring rate K. And that gives us 19.64 divided by 4.27, which gives us a figure of 4.6 turns. So 4.6 turns of the barrel for 120 psi, going back to our imperial units again here, safety relief pressure. 4.6 millimeters this is giving us, which because of the pitch and the lead translates to 4.6 turns. So what we're going to do now is we are going to do this for real live, and I might end up with egg on my face, so let's see if the theory works. Okay, so here are all the pieces of the little system we've been analysing. We've got the M12x1 threaded adjuster barrel, the spring and the poppet. So we'll assemble this now and we'll pump it up and see what happens. So put the poppet in with the spring, put in the barrel, and we'll just engage this thread and get it started. Okay, so all that's done is just taken up the slack there and just snugged the spring. It's not put any compression, appreciable compression on it. So we're going to go for the 4.6 turns now. So that's half a turn, that's one turn, 1.5 turns, 2 turns, 2.5 turns, 3 turns, 3.5 turns, 4 turns, 4.5 turns, and a fraction more for 4.6. We'll leave the jam nut off for now. We'll get the little drip tray in, and we'll get this so you can see the gauge like that. There we are. Okay, it's worth noting at this point that we're using an incompressible medium to pressure test this. So if we have an issue, we'll just get a leak rather than using a gas like air or argon where we'd get an explosive release of pressure. So this is the safest way to do it without any shadow of a doubt. Okay, so let's pressurize it and see what we get. Nice and easy as we get closer. So that's 130 psi it went there. Now I am quite pleased with that, because I would say that that is within 10% of the value I was after, and given that this is not the absolute counsel of perfection, and neither is this, I think that's a good result considering where we're going with this. So I'm going to call that a win. So what we can do now is we can fit this back onto the compressor and be safe in the knowledge that we're going to blow off at the right pressure. Well, that's the end of my second video, and I hope you enjoyed it. I'm willing to concede that the approach I took with that little valve was way over the top, but I wanted to use it to illustrate the use of engineering principles and calculations in the workshop, and how we can use them to help us when we're designing or making something. And that's the route that I want to go down when I go on to making bigger projects and more complex projects as we progress. Now, the time has come for me to say to you, have a very Merry Christmas and a Happy New Year, and I hope to see you in 2022, and let's hope it's better than 21 was. So take care, and if you enjoyed this video, please like and subscribe and share. And please leave me a comment, it'd be great to hear from you on what you thought of the video. Take care.